Okay, hello everyone. Welcome to this week's Astro seminar. We are delighted to have with us Ben Margalit, who's currently at Berkeley. I met him briefly as a master's student at the BIU. He later went on to do his PhD in Columbia and is now in the third year of his postdoc at Berkeley. And Ben will tell us about multi-messenger astronomy and its constraints on neutron stars and nuclear matter equation of state. Go ahead.
It is quite a tongue twister. Thanks, Elfik. Well, hi everyone. Yeah, it's good to be able to visit Israel, even though remotely. Unfortunately, it's been a while. It's almost a year since I've actually flown in and visited in person. So yeah, I'm happy to be here and tell you a bit about using multi-messenger methods, looking at binary neutron star mergers to constrain the properties of dense nuclear matter. And that sounds like a very complicated and dense title. And so I'll try to unpack what that means in the next beginning of this talk. And I sort of prepared this, much of the first slide at sort of an introductory level, thinking that there are probably students in the audience. And so please, if you have any questions at any point, just stop and ask. You can write them in the chat, though I can't guarantee that I will necessarily see it. Zoom is weird in that sense, so feel free to just unmute yourself and interrupt. I'm happy with that as well. All right, so wait, Ofik, before I go ahead to my next slide, just to make sure, should I stop after 50 minutes or so, or let me know when you can stop?
It's not very tight, but between 45 to 55 minutes, and then questions.
Sounds good. All right, because I probably have too much slides, but I prepared to skip things, so I'll just stop then. All right. So basic outline of what I will try to go through, and it's really, the point is not to go through everything. The point is just to have more of informal, interesting conversation where people can learn and ask questions. So I'll start with some intro just about neutron stars and dense nuclear matter, then talk about different astrophysical messengers and in particular gravitational waves. Then the highlight of talk will be on binary neutron star mergers. And from there on, I'll talk about ways we can use these interesting events to learn about fundamental properties of matter. Okay, so starting with the basic intro. So what are neutron stars? You might ask. That's the first thing that I believe I have somewhere in my title. So these are basically the ash left over after the explosion of massive stars. So massive stars end their lives in dramatic explosions that we often observe as supernovae. And one of the possibilities is that the remnant of this explosion is a neutron star. And what you see here on the right is an actual image, a real image of a neutron star. This is a false color image. This is not an optical, this is an X-ray image, but nonetheless. And this is an image of the famous Crab Nebula, which was associated with a supernova that exploded, I believe, in the 10th century or so.
11th
and
century.
That 11th, thank you.
1054 is 11th century.
Excellent, good memory. And that dot you see right smack in the middle is an X-ray image of this neutron star. And all the stuff you see around that's a separate, you can have a whole separate talk just about that, but we'll not focus on that at the moment. Okay, so these are the ashes of supernova explosions of massive stellar evolution, but that still doesn't tell you what they are. So the interesting thing about neutron stars is that they're very small by astronomical standards. So here you see, very familiar classic image of a neutron star, more or less to scale next to Manhattan. So their sizes of order 10 kilometers or so, but they're extremely massive. So in that 10 kilometers, you pack an amount of mass that is of order the mass of our own sun. So a canonical neutron star would be 1.4 solar masses, but we know that they have a range of masses. Some even go up to 2 or so solar masses. So if you have so much mass in such a small region, that immediately tells you obviously that they're very dense. And in giving public lectures, we often use these types of analogies. So if you were able to scoop a quarter teaspoon of neutron star matter and hold it in your hand, it would mean way more than the total island of Manhattan. So this is just some popular kind of image to get an idea. Okay, so more quantitatively for us, the densities we're talking about are upwards of several times 10 to the 14 grams per centimeter squared. Now, why did I put this, seemingly very precise number, 2.7 times 10 to the 14? What is this 2.7? Why do I care that it's 2.7? Well, this is an interesting number because that is the so-called nuclear saturation density. So what I'm showing here on the right is a plot of the density in units of 10 to the 14 grams per centimeter cubed of nuclei, atomic nuclei. And you can see here various atomic nuclei, calcium, cobalt, and so forth. And what you see is their density as a function of radius. And the interesting thing is that basically all nuclei, from the lightest to the very heaviest nuclei, they all have more or less constant density in their interior. And that density is roughly this number, the so-called nuclear saturation density. Okay, so that's an interesting property of nuclei in nuclear matter. And the interesting thing about neutron stars is that the densities in the interior of neutron stars exceeds this value. It can exceed it quite significantly by factors of several to maybe even 10. And so because of this, we actually don't know what the composition or behavior of matter is in the interior of neutron stars. So here is a cross-section, a cartoon cross-section of a neutron star. You can see on the left density scale, all the way from the lowest densities at the exterior of the neutron star to the highest densities of order 10 to the 15 gram per cubic centimeter in the interior. On the right, you can translate that into radius, and you see that, for much of the neutron star, its outer core is composed of just neutrons and a little bit of protons, electrons, maybe muons, and things like that. But the interior is really just a question mark. And the reason it's a question mark is that we don't have matter in these conditions anywhere on Earth. We don't have that naturally, of course, but we can't even reproduce them in the laboratory. So the closest we can get to are heavy ion colliders, where you smash ions with one another and produce increase the density, at least very briefly. The problem with that scenario is that you also have very high temperatures. When you smash these ions together, they're very hot. And that's very different from the conditions in the interior of neutron stars. And so there's no way to directly study the composition and or behavior of matter in these conditions on Earth. And so neutron stars really provide a unique laboratory to learn about fundamental physics in this respect. All right, so how do we learn about the fundamental physics of neutron stars? So I showed you this cartoon, right? But I have this region of red that's a question mark. I showed you these cartoon teaspoons where you could maybe scoop up neutron star matter if you're imaginative, if you write a sci-fi novel. But as we know, we can't actually scoop up neutron star matter with a spoon and study it under a microscope, right? So how do we study the microscopic behavior of neutron star matter? Well, the nice thing that comes to our aid here is the fact that the bulk properties of neutron stars, so things that potentially are measurable, the masses of neutron stars, their radii, are related to the microscopic properties of dense nuclear matter.
Ben, can I ask?
Yes, go ahead.
Hi. Previous slide, please.
Yes.
It's a calculation question, but maybe from the top of your head, how the red area, how far it from the Schwarzschild radius of its own?
So neutron stars, I should say, that's a good question. So neutron stars do not have an event horizon, so they do not have, you don't have a Schwarzschild radius inside the neutron star. So I guess maybe what you're asking is, if you imagine that you took this 1.4 solar mass of neutron star and asked what would its Schwarzschild radius be? Well, it would be a couple kilometers or so.
So
probably knows the exact number off the top of his head, but I think maybe like 3 kilometers or so.
So I cannot have a black hole inside the red area because I have density that is enough and radius that is small enough also?
So the reason you don't have a black hole, you don't actually have an event horizon at this, what you would naively say was the Schwarzschild radius at 3 kilometers. Why? That's a good question. Why don't you have a black hole there? The reason you don't have that is because of Birkhoff's theorem. And so basically what you need to account for is the fact that there's a lot of mass outside of 3 kilometers.
Okay.
So most of the mass of the neutron star is contained outside of that radius. And so if you were to ask, what is the Schwarzschild radius of only the amount of material contained within 3 kilometers, that would be less. And then you'd calculate a smaller Schwarzschild radius. And you can do that more and more, and you'd see that you never have a horizon.
Okay. Okay, thanks.
Great. All right, excellent. Thanks for the question. So I was telling you that you can study the microscopic properties of neutron stars and neutron matter by observing bulk global properties of neutron stars. And this is basically the cartoon schematic showing that. So the idea is that you can invert or you can relate in a one-to-one relation the pressure versus radius diagram. I guess in this particular figure from Lindblom, this is plotted as density versus pressure, but I guess the physical way to think of it is pressure versus density. You can relate that to a mass radius diagram. And so basically for a given equation of state, for a given curve in this plane, each equation of state corresponds to different pressure at some density, just due to the microscopic interactions of matter. So for a given curve in this figure here, in this panel here, you can calculate what is the structure of neutron stars, and you'll find that different neutron stars of different masses will have different radii. So that's a mass radius curve. And the way you do this inversion or this calculation is basically you solve the so-called TOV, Tolman-Oppenheimer-Volkoff equation, which some of you are probably very familiar with or might have already seen. And this equation here in the bottom, the details are not important. This is basically hydrostatic equilibrium. So a generalization of the usual hydrostatic equilibrium equation to general relativity. So if you're really interested, you can just convince yourself that all of these terms in parentheses that have c squared in them, those are sort of the relativistic corrections. And if you cancel those, if you say, well, c squared is very large, I mean, the Newtonian regime, can forget about this term, forget about that term, forget about this term, this is 1, then you just have gm rho over r squared, which is the regular Newtonian hydrostatic equilibrium equation. So the point is to solve this equation, the only thing you need to specify is p as a function of rho. Once you specify that function, the so-called equation of state, which depends intricately on the fundamental properties and interactions of matter at these densities, then I can solve this equation and tell you what the structure of neutron stars is. So here's another mass radius diagram. This is from a review paper by Ozon and Friere. And this is showing the same thing. So again, what's plotted here is the mass of a neutron star, or I should really say the radius of a neutron star with a given mass. So say I want to construct a neutron star that weighs 1.5 solar masses, and it has this black equation of state. I would then say that its radius is, what is this, about 10 kilometers. If on the other hand, I used a different function, p as a function equation of state, so p as rho was a different equation, say the green one, then I would say that the radius of 1.5 solar mass neutron star is 14 kilometers. And so that's the name of the game. The name of the game is that different equation of states correspond to different curves here. And if we can measure a bunch of points in this plane of mass and radius, these are properties that are actually measurable, and I'll discuss a bit later how they are measurable. But masses of neutron stars are measurable in many different ways, and radii we're only now starting to probe. So if we're able to measure that, then we can potentially rule out some of these equations of state and learn about fundamental physics. So that's the name of the game.
I just want to add here, the curve for black holes at the top left corner is precisely what Max was asking about before. you can see that at a given radius, the mass of a black hole would be much higher than than any equation of state for that same mass. Equivalently, at every given mass, the radius of a Schwarzschild black hole is much, much smaller than any of these equations of state would give you for a neutron star.
Right. Excellent. All right. So I've tried to unpack at least the first part of the title of the talk, which is dense nuclear matter and neutron stars. So that was sort of the intro part on that. So another term that I've used in my title was multi-messenger. And many of you have probably heard this term many times, and hopefully all of you are familiar with it to some extent, but maybe some of you haven't heard really what that means. And so just a quick intro into what multi-messenger actually means. And so the idea is that there are actually many different messengers, for lack of a better word, that we can use in astronomy to study various systems. And really there are 4 different messengers that one can think of. And if you focus on the top left, then that is, the classic electromagnetic messenger, right? So basically these are electromagnetic observations. Optical would be sort of classic astronomy, but of course there's plenty of radio astronomy, X-ray telescopes, gamma ray satellites, infrared. So throughout the entirety of the electromagnetic spectrum, we have, or for most of it, we have various different telescopes and facilities that are observing the sky. And this is sort of traditional astronomy. But we also know that besides electromagnetic radiation, various astrophysical sources can produce other types of messengers that can arrive to Earth and can potentially be observed. So neutrinos are another famous type of messenger. They're created in many different circumstances, for example, in nuclear reactions in stars and in our own sun, in supernova explosions. I won't talk about neutrinos in this talk though. Cosmic rays are another famous example of a messenger. Really, this is just matter, right? This is just particles. So actual advection or flux of particles that's reaching the Earth. This is just nuclei of different material. Again, I won't be talking about those either. But the 4th messenger, which is particularly exciting, especially in our current age, are gravitational waves. And I'm showing here the contraction of an expansion of space-time as gravitational wave passes through a given point in space. And this is sort of a cartoon picture to illustrate that. So when we say multi-messenger, what we mean is that maybe we have the potential of observing a single event or a single object, astrophysical object, with more than just one type of messenger, with say both electromagnetic observations and gravitational waves. And using different, different goggles to observe the same event can really teach us something profound about the event that we might not see with only one type of messenger. So I won't go into the details of gravitational waves because I know that many of you here are probably experts far more than I am, but many of you have also heard Ofek, I think, talk about this recently. But gravitational waves are primarily produced in compact object binaries. And so if you ask what astrophysical object produces gravitational waves that we can then detect, and we are now detecting with gravitational wave detectors on Earth, well, these are binaries. So binary systems where 2 stars, and then they have to be compact stars. So here compact can mean either a black hole or a neutron star, which will be relevant for our case. So when these 2 objects orbit one another, and they're very close to one another, then they emit gravitational waves. And that emission of gravitational waves basically takes away energy from the binary. And if you take away energy from the binary, well, then the binary basically loses energy and it comes closer together. And as it comes closer together, well, actually what happens is that it emits more gravitational waves. And then you release more energy and you come closer together and henceforth until you get a so-called merger of the 2 objects. They come into contact or tightly disrupt one another, but they cease to be 2 separate objects. And the nice thing about these gravitational waves that I'm sure all of you know is that they have only very recently been detected and are now being detected at a very regular rate, at least for black holes, by the detectors, the gravitational wave detectors built in Livingston and Hanford, the LIGO detectors, and also the Virgo detector in Italy. So the takeaway is that gravitational waves are a new form of astrophysical messenger. Well, new in the sense that we've only started observing them very recently. And they particularly probe compact object binaries, so binary systems that can contain neutron stars that orbit one another. And so that's the length of why they'll be interesting to study dense nuclear matter. All right, so usually when people analyze the gravitational wave signature of compact object binaries, whether it be black holes or neutron stars, what you do is you basically construct a waveform, which is the thing that is detectable by LIGO. And the leading order of that waveform can be described by just 2 point particles orbiting one another. But in reality, finite size corrections actually do come into play at higher order. So one way to think about this, for those of you who are familiar, is that you can do this so-called post-Newtonian expansion, where you basically expand in powers of velocity over speed of light, so v over c. And if that term is very small, if v over c is small, then you can write an expression for the gravitational waveform. And at high order in v over c, I think this is fifth post-Newtonian order, the so-called tidal correction comes in, and I'll describe what that tidal correction is. So the idea is that maybe we can use this potentially we can use this small finite size correction to the point particle waveform to actually learn about the size, right? The whole idea is that a finite size correction depends on the size of the object. And so maybe this can teach us something about the radius of neutron stars, which, as I showed earlier, is important for constraining dense matter. So how do we do that? Well, the gravitational wave signal really depends mostly on the mass quadrupole moment. And what happens is that when you have an object that has a finite size, like a neutron star, it is tidally deformed because of the tidal field or the gravitational potential of its companion. And as it's tidally deformed, you actually increase the mass quadrupole moment. And so here's a cartoon from this paper showing, an isolated neutron star that just is spherical and has a radius r. But if you put that neutron star in a tight binary, or rather if you put it near a companion that's very massive in a deep potential well, then you actually deform the neutron star. And that's just a tidal effect. So one side of the neutron star is being pulled towards its companion more strongly than the other side. And as you distort the neutron star, it becomes oblate, and that actually increases the mass quadrupole moment. So all of this is to say that if you have a tidal effect, if you have these finite size effects, they're combined, what they combine to do is that they combine to make the binary merge quicker. So they increase the mass quadrupole moment, they increase the emission of gravitational waves, and therefore the binary merges quicker. And the term that's important for this is the so-called tidal deformability term, which is proportional to the radius to the fifth. So it's very sensitive on the size of the neutron star. And just to illustrate what I just said, here's a gravitational waveform. So this is the amplitude of the gravitational wave as would be detected, say, by LIGO as a function of time. And as the binary inspirals and loses energy, the frequency of this wave increases, and eventually at the end, towards the very right, you get a merger over here. And the point to show with this figure is that if this lambda parameter is 0, basically if we're doing the point particle estimate, they merge at this time. But if you have finite size effects, if you have a neutron star that has a significant radius, then such as the blue curve, it'll emerge quicker, which is just what I told you now. You'll drain more energy from the system and you'll emerge quicker. All right, so this is a way that we can potentially probe the sizes of neutron stars. So I haven't prepared, actually, I should have prepared some slides of introduction about GW17817, but I'm sure many of you, if not all of you, have already heard a lot about this event. So GW17817 is
Can I stop you for a second? Can I ask you a question?
Yeah, absolutely.
Isn't that degenerate with the spin of the neutron stars?
Yeah, so there are a couple of other effects that come into play that can also cause the binary to merge faster or not as fast. And so, right, there's spin orbit coupling, there's spin-spin coupling, there's mass ratio. So I believe for this calculation, I would think that the assumption is that these are equal masses, non-spinning neutron stars, and just playing around with this one parameter. But you're right that there is a degeneracy. Now it's not a perfect degeneracy. If you had perfect measurements of the gravitational waveform, then these wouldn't be degenerate, but in reality they are.
Can you estimate what is the size of this effect, relative to the, let's say, spin orbit coupling that you may have?
So let's see. So the classic degeneracy that people talk about, or is very apparent if you look at any of the LIGO data, really, in any of the LIGO detections, the classic degeneracy is between spin orbit coupling, or spins in general, and mass ratio, because those are higher order terms. So they come at higher order than tidal effects. So tidal effects is actually much smaller than both of those terms. And so usually what people talk about is this degeneracy between spins and mass ratio.
Right.
And again, those are dominant over the tidal effect.
Okay, so the tidal effect that you show here could actually, it's not really practical within current.
Well, it is potentially feasible, but you need a very strong signal. You need high SNR. So as I'll show in a minute, even for GW17817, which had an enormous signal to noise ratio, was very, very loud event. There's actually no detectable tidal effect, but you can still put interesting constraints. You can still say that the tidal effect must be less than some number, otherwise it would have been seen.
Yes.
So I can probably say more about this.
I'll add that there is a degeneracy in general, which could be large. The tidal effects can be masked by spin and mass ratio, by spin and mass ratio. But for neutron stars, you actually have typically good constraints on the spin and mass ratio. For a BNS system, your mass ratio cannot be very different from 1. Right? It's something between 1 and 2, because you're talking about 2 neutron star masses. And the spins we expect to be quite low as well. You don't really see a neutron star spinning as fast as a black hole, because it would start centrifugally shedding out matter. So in principle, the terms are of higher order, but in effect, when you put in neutron star parameters, you can gain a little by reducing the actual effect.
I think you won't gain an order of magnitude.
What?
I think it will. I don't think you'll get orders of magnitude. I'm not sure how many orders of magnitude you have here. I agree with you that as far as the mass, yeah, you don't have much to play with. But as far as the spin, okay, you won't get into 0.9 something, well, not 99, but I think you can. Neutron stars can be with substantial spin.
I think 0.7 something is the breakup.
So if you have 0.5 or so, what effect will that give you relative to this effect that you see here?
It might be 1 order of magnitude, because I think the effect is not linear in the spin, and if it's quadratic, you already gain about 0.2 or something like that. But
yeah, I would in fact expect that most neutron stars to have a spin of some kind, given the way that they were born.
Yes, but
the thing with spins though is, another point with spins. So the effect, just going back to the fact that these aren't perfectly degenerate, right? So if you have high spin, if you were to postulate that neutron stars are maximally spinning and have 0.7 spin, then presumably you would also see precession, and they're not perfectly aligned. Then presumably you would also see precession in the waveform. And so again, this is just to point the fact that they're not perfectly degenerate. So there are ways to distinguish between the effects.
Okay.
All right. So this spectacular event that was discovered in August 2017. So this was the first merger of 2 neutron stars that was detected in gravitational waves. And it was really a watershed moment. gained, it made a very big push and sort of splash in the community. And there were many papers written on this event and still papers being written at the moment. So what can we learn from it? I was telling you that we can potentially use these tidal effects to constrain the size. So what are the results? So here's one example. This is from a LIGO paper in 2018, showing the constraints on both mass and radius in this mass radius plane obtained from GW170817. And so the blue and orange shaded regions are the regions that are constrained for this particular merger by LIGO. That's just one example. This is another example. This is a recent paper that I was involved in, led by Colin Capano. And you can see here also constraints on the radius compared from our particular study compared to other studies. And the details aren't important. The point is the following: the fact that there was no measurable tidal effect for 170817, as the stuff just mentioned, right? It's a very small effect. And even for this event that was very close by and had a huge signal to noise ratio, we couldn't detect tidal effects. But the fact that we didn't detect this tidal effect means that the size of the neutron stars can't be too large. If it were, then we would have detected it. So it places an upper limit on the radius. And more quantitatively from 170817, the numbers that we get that people have gotten in the literature are that this upper limit on the neutron star radius are about 12 to 13 kilometers. And there is an immense amount of literature on this topic. So that's the first way you can constrain neutron star radii using gravitational waves. And this is very exciting because this is almost a direct constraint on the radius, with the caveats of, what you're really constraining is the tidal parameter, which is a proxy for the radius, but there's some other things involved there too, and with the fact that there are degeneracies with other parameters, as the stuff mentioned. But hopefully, if people do correct full Bayesian analysis, then the degeneracies are taken account to in the posteriors. But of course, that depends on the details. So we can put an upper limit on the radius, and this is using gravitational waves alone. Where does the multi-messenger come in? So now let's transition to thinking about multi-messenger methods of constraining the radius. So for that, we need to talk a little bit about electromagnetic counterparts to neutron star mergers. So actually, there's an immense amount of literature that had theorized that neutron star mergers would produce a variety of electromagnetic counterparts. And this far precedes the detection of this event, GW170817. And so this is just one cartoon schematic showing a number of these potential electromagnetic counterparts. And this is not a complete list by any means of the things that people sort of envision. And sort of the main things that have been talked about a lot in the literature are gamma ray bursts. So that's this thing. These are events that have been known for a very long time, since the late 60s, events where a huge amount of energy is released in gamma rays from cosmological distances, and there can be many separate talks just about gamma ray bursts, but I won't go into them. The point is that one subclass of these gamma ray bursts, so-called short gamma ray bursts, had been postulated to arise from the merger of two neutron stars already since the late 80s. And the other type of electromagnetic counterpart that people have talked about extensively are these things called kilonovae. And the name of these objects really just says that these are, of these events really just says that these are optically emitting or perhaps infrared emitting events that are similar to supernova in the sense that, you get a rise and drop in the light curve. They're powered by radioactivity of matter. So in that sense, they're similar to supernova, but they're very different because the composition of matter is completely different. And I won't go into the details of that, but the point to remember, the takeaway is just that from neutron star mergers, it is expected that you can get an optical or near infrared transient that lasts about a week or so and is relatively dim, but potentially detectable. And then there are many other types of other counterparts, from UV to radio and X-rays that I won't go into. So the point is that there are many different electromagnetic counterparts that can that come with neutron star mergers, and you can get a variety of different counterparts that can change in properties depending on the result of the merger. And this is a messy process. And the only reason this is possible, you may ask, well, why don't we have the same thing for binary black hole mergers? The only reason we get such a long list of counterparts, or we expect to get them, is because there is matter involved. So all of this light is being produced essentially by ejection of matter in various different forms, in jets or in winds or in ejecta. And if you had binary black hole system with no matter involved, then you wouldn't have any matter to eject, and that would be able to shed light afterwards. So how can we use these electromagnetic counterparts? So this is what we actually observed, or people actually observed for GW 17817. This is from the famous or infamous paper that had just 3,000 or so authors and many collaborations. So this is LIGO-Virgo collaboration, of course, but also with basically every single observing telescope and collaboration you could possibly imagine. Everyone pointed their telescopes at this event, and many of them observed it. And so this schematic from that paper shows the different observations of GW 17817. So the first, in terms of time size, you go from left to right. You basically go from the time of merger, which is here, to late times after merger, which is to the right. So the first thing that happens is, of course, the gravitational wave event that's detected by LIGO. That's shown in this spectrogram. There was then a flash of gamma rays that was detected by Fermion integral. And then later on, there was an optical detection of the kilonova, along with X-ray detections of the afterglow of the short GRB and radio and so forth. And I won't go into the details, but this is just to show that the single event was detected in many different wavelengths, in both in electromagnetic and in gravitational waves. So perhaps you can then ask, well, perhaps we can use this multi-messenger approach that I've been talking about for a while. We can combine gravitational waves and electromagnetic observations to learn something new about the equation of state that we couldn't learn from just using one of them. And indeed you can. And so I'll go through the methodology, the basic idea of one way of how we can do that. And so to understand the methodology, we have to understand a bit what happens after the two neutron stars merge. So here is sort of an anatomy or a schematic of a neutron star merger. You have the two neutron stars, these two blue objects orbiting one another, they in-spiral, they lose energy to gravitational waves, and eventually they merge, meaning they totally disrupt and or touch one another, collide with one another. And the point is that what happens afterwards will depend primarily on the mass of these two objects and on the underlying equation of state. Another way to say this is if I were a computational astrophysicist, if you wanted to simulate the system, the only thing you need to do to simulate the system on a computer is you need to provide initial conditions. So you need to say what the masses of the neutron stars are. Perhaps you also want to play around with the mass ratio, spins, various other things like that. But say you forget about those smaller effects for a moment. The main thing you need to fix is the mass of the system. That's the initial condition. And then you need to tell your code what is the equation of state. That will determine the hydrodynamics and the structure of the neutron stars. Once you set those two things in your code, you can just let it run. So nature does more or less the same thing, right? It just depends on these initial conditions and on the fundamental equation of state. So this is what I'm showing here. What I'm showing here on the right is an axis of mass. So this is the mass of the total binary. So if these binaries weigh more, they'll be on a scale higher up here on the scale. And the second thing I'm showing are these different cuts, different mass points, which are delineated by this so-called TOV mass. And this mass is basically, as I'll show in a minute, the maximum mass that a regular cold non-rotating neutron star can support. So it turns out that for any given equation of state, neutron stars can only be supported up to a certain mass. And above that mass, if you try to add more mass to that neutron star, it will collapse to a black hole. So If the two neutron stars that merge are extremely heavy, what happens is that immediately upon contact within a dynamical timescale, which in this case is milliseconds or less, they'll collapse the black hole. This is called the prompt collapse scenario. Another option, if the neutron stars are slightly less heavy, is that you form an object that is metastable. So it's stable for a short amount of time, but longer than dynamical timescales. And the reason this metastable object is metastable and doesn't immediately collapse the black hole is just because of rotation. So there's a lot of angular momentum involved in the merger. And so the remnant, this post-merger remnant, can rotate very quickly, and that can add some support, centrifugal support to the object. But if you let this system evolve in time, that once it loses its centrifugal support, it can collapse. And that can happen either through loss of, through viscous processes, through loss of differential rotation, or through actual spin down and loss of total angular momentum. And again, the details are not important for this talk. But the last possibility is that you actually produce a stable neutron star, meaning that, if I went back to GW 170817 now, and I looked at it, there might be a neutron star still sitting there that survived the merger. And the only way that's possible is if the mass of these two initial neutron stars, the combined mass of the system, is less than the so-called TOV mass, meaning the combined mass of the system, if I add the two, minus small amounts of ejecta material and things like that, needs to be less than the maximum mass that's supportable by my equation of state. So this will only be possible for certain equations of state, but not possible for others. So how can you use this to constrain the equation of state? Well, all you need to remember is the following heuristic. Basically that the merger outcome, one of these four possibilities, depends on the mass of the system, total mass of the system relative to this TOV mass, which is a proxy, or I should say an indicator of the equation of state. And the first of these things, the total mass of the system, we know very well from gravitational waves.
Yes. What fraction of mass can theoretically be ejected outward in the form of an accretion disk?
So that's a good question. So some recent work in the past couple of years has shown that if you form a disk around these, the post-merger object, which we think for 170817 certainly did happen, then roughly 40–50% of that disk mass can be injected in outflows. Now the next question you can ask is, what is the mass of this disk? And typical numbers that people talk about are maybe 0.1 solar mass or so. And it could potentially be much less depending on the type of merger.
Can it be much more?
It can be significantly more. No, it might be, it might be 0.2 or 0.3 solar mass, but no simulation has found anything more than that.
So you're basing that on simulations of mergers with a given equation of state?
Yes. Yes.
Because I would imagine this should be strongly dependent on the equation of state that you're assuming, as well as other conditions.
Correct.
The spin. If your spin is close to the maximum, then you might actually get a lot of mass loss.
Correct. So most of the simulations probe the regime of no spin, zero spin or very low spin. So that's one caveat. As for the different equation states, there's actually, at this point, people have simulated these events with quite a variety of equation of states. And as I can show later, I have a figure actually answering this very exact question of what is the disk mass as a function of equation of state. And you can actually you can parameterize this in a relatively easy to understand way. And perhaps maybe I'll jump to that just because you're asking. Here it is, yes. So this is basically your question. So this is the disk mass as a function of some parameter, and this parameter is basically, as we showed in our work, but others have parameterized it a bit differently, is a measure of stability of the object. So if you're above 1 or about 1, the object immediately collapses or promptly collapses to a black hole, and you don't get very much disk mass. Basically, all of the disk mass that you have is tidal ejecta, which is not much. If the remnant survives for longer and doesn't immediately collapse to a black hole, then you get a dramatic increase in the disk mass, but it saturates, and it saturates at about, well, I guess this is 0.2 solar mass or something like that. And here, this is just for 4 different equations of states, but people have simulated this with many other equations of state as well.
But with slow spin.
Yes, you're right, slow spin, or zero spin, I believe, actually, in most cases.
Okay.
Also equal mass. So binary mass ratio can affect this as well. And that actually has been looked at more. So there's recent work by Kenta Kikuchi that has looked at that. And also Andy Baustein just had a recent paper about that.
Okay, thanks.
That's going to actually reduce the mass of the disk, right?
So what is going to reduce it?
If one of the objects is smaller than the primary, it will only reduce.
No, actually it increases the amount of the disk because you can tidally disrupt one of them before they actually shock and come into contact. So if you have enough of a mass ratio, you can get a tidal disruption, which really creates a huge amount of mass in ejecta and disk. All right, I know I'm running out of time, so let's see. I'll go through some of this quickly. So we were here, I believe. So I was telling you that the outcome really depends on the mass of the system and the equation of state. And the mass of the system is very well measured directly by the gravitational waves. So here, this is an expression that just showing that the total mass depends on the chirp mass, which is precisely measured, and the mass ratio, which is less well measured, but this function actually turns out to be a very weak function. So even if you let this thing vary from 0.5 to 1, then this will only be a 2% effect or so. And that's actually exactly the 2% you see in this number from the LIGO paper, where the total mass as determined by LIGO has a 2% uncertainty, while the chirp mass has, I don't know what this is, but it's measured to almost infinite precision, or to very, very high precision. So the gravitational waves tell us very well what this total mass is. So where does the multi-messenger come in? The multi-messenger comes in from the electromagnetic observations. And without going into the details, just in a qualitative sense, I'll say that the electromagnetic signature, the type of signatures you can get, can depend quite sensitively on the fate of the remnant, whether it lives for a long time or it collapses very quickly. And so you can try to make these qualitative distinctions between different types of remnants, whether it was long-lived or promptly collapsed or somewhere in between, based on the types of electromagnetic signatures that you have, and learn something about this. And again, the details aren't important. The point is that you can try to make this qualitative statement without going into quantitative details about exactly what is the number of how much ejecta mass was, or how fast the ejecta velocity was, and things like that. So then if you know these two things, well, by this heuristic relation, you know this term, you know that term, well, that immediately tells you that you can learn something about the final term. In this case, the maximum mass of neutron stars, the TOV mass, which tells you something about the equation of state and about dense nuclear matter.
Is this is this one-to-one correspondence, or do you need to collect big statistics to be able to tell this part?
No, it's a one-to-one correspondence. Yeah. So what does this tell us for GW170817 for this particular object? Well, there have been many arguments given in the literature that rule out the scenario where this event produced a long-lived remnant. So one that was in either of these two categories. And the main reason, an argument that's been given for that, is an energetic argument, in the sense that if you had a long-lived remnant, then there's a huge amount of rotational energy in this remnant. And that energy, by definition, is released over spin-down timescales in these two scenarios. And it would have been observable in one form or another, and yet it wasn't. And so that rules out, that's one way to rule out those scenarios. There are other arguments as well. And so if you take that argument, if you rule out these two scenarios, you can place an upper limit on the maximum mass of neutron stars. And I'll just show that in the following way. So here's our mass scale, the same mass scale I showed earlier. And here are the different cuts. This is the maximum mass, the TOV mass. And here's these other cuts for the other types of remnants. So say I want to plot where GW170817 falls. Well, the total mass for GW170817 is about 2.74 solar masses. So perhaps it falls here. But as I just argued, these two scenarios, the supermassive neutron star and the stable neutron star scenario, are ruled out. So that doesn't work. So what can we do? Well, I can't change the mass of GW170817. That's just measured by LIGO, right? That's a known thing. So I don't have any freedom in changing that. What I do have freedom in changing is the position of these blue curves. So I can move these blue curves down and make this compatible. Now you can ask, well, how am I moving these blue curves down? That's saying that I'm changing the equation of state of nature. Now, obviously, I'm not actually changing the fundamental properties of nuclear matter. What I'm doing is saying that there's an uncertainty in those properties, and therefore we don't actually know where these blue curves are. But by adjusting the location of these blue curves, which are unknown, we can make GW170817 compatible with this argument. And if you do that, you see that this is ruled out, this is allowed, this is ruled out, this is allowed. That basically provides an upper limit on the TOV mass. And for the case of 17817, the numbers that we get are about 2.2 solar mass or so, maybe a bit above that.
Why is it an upper limit and not the lower limit?
So if you go back to this, look at the bottom blue dashed curve at this one.
Yeah.
Look, and you'll notice that as I move from the not allowed to permissible region, TOV goes down. So this is not allowed. High TOV is ruled out. Low TOV is okay.
Okay. So now, when you say that they don't exist for a long period, there was this 1.7 seconds delay. So what is the long period that you're referring to? How long is long here?
So long means over longer than viscous timescales, over spin down timescales. You basically need to tap into the rotational energy of the remnant. So if you collapsed immediately after viscous processes redistribute angular momentum and you lose rotational support, then that's fine because you haven't lost any bulk or total angular momentum or energy, spin energy. Now, quantitatively what that number is, well, that's sort of uncertain, but people generally talk about, hundreds of milliseconds as characteristic of viscous timescales. And spin down timescales can be anywhere from seconds to, much, much, much longer, depending on what you assume of dipole magnetic fields and things like that.
Right, but you did say the 1.7 delay between the merger and the GRB. So presumably you do have this time for a spin down if you want to associate it with this merger.
So if the argument, yes, so that's a separate argument though, I agree. If your argument is that in order to produce a GRB, you have to have formed a black hole first, which is a very reasonable argument. And that's the only argument you provide, then you have this wiggle room of 1.7 seconds. But I think the stronger argument is to forget about GRBs and jet launching physics, and just think about the energetics of the event itself. If you argue that you had an object that lived for that 1.7 seconds or for any amount of time, it really doesn't matter if it's 1.7 seconds or if it's 3,000 seconds. If you had an object that lived over these spin down timescales before it collapsed, then you would have injected 10 to the 53 ergs of rotational energy in one form or another, either into jetted outflow or into the disk winds, as opposed, or into pulsar wind nebula. And in any place you look, you don't see that energy. So that's a bit of a separate argument.
Can it be in the form of sort of a hidden energy in magnetic fields or neutrinos that you don't see?
So neutrinos take very little of the spin energy. The one option that people have been arguing for is gravitational wave spin down. So if you spin down through gravitational wave losses instead of electromagnetic spin down, you can hide that energy. That would not be detectable by LIGO for this event. But I think there are strong arguments why that seems very difficult to do. You need the neutron stars to be, the remnant to be very deformed, very large ellipticity, which no one has showed is possible to actually produce.
All right.
Okay. Ulfik, I'm looking at the clock and I see that I'm basically out of time. So should I skip to my summary? I mean, I have plenty more, but I don't, that's the point is not to get through all the points.
5 minutes to cruise to the end.
Cruise. All right, let me think then what I want to do before I go to the summary. I guess I'll briefly mention these constraints then too, without going into the details too much. So I showed you that you can use multi-messenger methods to get constraints on the maximum mass of neutron stars. You can also use multi-messenger methods to get different constraints, complementary constraints of the neutron star radius. And one way to do that, which was argued first by Andy Baseline, is if you rule out this scenario. So if you rule out the prompt collapse scenario, which there is an argument for in the case of GW17817, then you can place a lower limit on the neutron star radius. And the argument for that in 17817 is a mass argument. And again, the details are probably too much in the weeds for this talk, but the point is that the kilonova that was observed to accompany 17817 was very bright, and so we infer a large amount of ejecta mass. And according to various arguments and to numerical simulations, you can't produce as much mass when you have a prompt collapse of the black hole. And so it turns out that if you rule out that scenario, you can say something about this value over here, this threshold. And the reason I have, a range of numbers here for this threshold is that this range of numbers depends on neutron star radius. And so if you can say exactly what this threshold is or what lower limit for that threshold is, you can place a lower limit on the radius. And that's what Andy Baseline did. So here the threshold radius is basically a function of radius in addition to the maximum mass. And if you go through the math and through his paper, then you can show that with addition of the causality argument can place a lower limit of about 10 kilometers on the neutron star radius. All right, so let me skip the multi-messenger stuff and skip to the summary. Okay, so here's our mass radius diagram again, right? So the point I think that I've tried to illustrate here is that binary neutron star mergers are really unique laboratories to study dense nuclear matter. I didn't go too much into detail about this, but I showed that you can use these events, these really exciting mergers of two neutron stars to study properties of neutron stars and therefore properties of dense nuclear matter. I didn't go into as much detail as why this is really one of the only ways to study dense nuclear matter. And again, that goes back to the point that this cannot be studied in terrestrial experiments. It also cannot be calculated from first principles. And so the only way to really probe this is in neutron stars. And one of the prime ways to study this in neutron stars is through their merger. And if you accept the fact that binary neutron star mergers are these really exciting laboratories for dense nuclear matter, then it should also immediately become apparent and clear that multi-messenger methods of constraining the equation of state are also really interesting. And the reason is that these are inherently multi-messenger events. Neutron star mergers, by definition, emit very strong gravitational waves, and we also know that they produce a myriad of different electromagnetic counterparts. And so these are, the quintessential maybe multi-messenger events, and if you're able to probe that dimension of two different messengers, you can learn something new. And I showed you two different examples, two different ways in which you can constrain the equation of state using multi-messenger methods, and one way where you can constrain the equation of state using only gravitational waves. And so to show this more quantitatively on this mass radius plot, if you think about the constraints that were placed on the equation of state from gravitational waves alone, these are using the tidal effects. These are sort of the constraints that people have given. So these red shaded bands are basically regions that are ruled out. These red shaded bands are the regions that are ruled out. So you can see the LIGO constraints and some other paper by Shumi Day that placed an upper limit on the neutron star radius, and don't worry about the lower limit for the moment. So that's one thing you can do with gravitational waves alone. But what happens if you ask, well, what about these multi-messenger methods that I talked about? Well, this is where you end up if you use these multi-messenger methods. And so I think what's clear from this type of plot is that you can really probe a significant portion of parameter space that is different and complementary to the one that you can probe using gravitational waves alone if you use these multi-messenger methods. And I think that's why this is a very exciting way to learn about fundamental physics using these exciting objects. And I'll stop here and take any questions. Thanks.
I have a question. Saf.
Yeah. Before the 1708-17, I think it was 2015, but I don't remember exactly the exact date. There was a neutron star which was seen with a mass, I think, 2.4. I don't remember the details in the top of my head. Who the paper was? Are you familiar with this case?
I don't know the particular object that you're talking about. So if you ask about the masses of known neutron stars, well-measured masses of neutron stars, there have been for a number of years now 2 precisely measured neutron stars whose mass is about 2 solar mass.
Mm-hmm. And there was
and one very recently measured neutron star whose mass is precisely measured to be about 2.13 or so.
Yeah, I think, if I recall properly, it was something like 2.4, but it's been a few years ago.
I think there are claims of higher mass neutron stars, but those are from my understanding, those are contentious. So the very precisely measured neutron stars are ones that are obviously in binary systems, and in particular ones that have Shapiro delay measurements, and then you can get the mass to very high precision. And those are the 3 that I just mentioned. So those are typically neutron star white dwarf binaries where you can get Shapiro delay measurements. There are different arguments for high mass neutron stars. I know from the Black Widow literature, where people model these systems, but that is quite model dependent in the sense that you have to really understand the messy details of the radiation, high energy radiation coming from these systems, and I've seen various papers claiming otherwise. So that's quite a bit contentious, I would say.
Okay.
I'll just say that we actually have a Black Widow talk in the seminar next week.
Yeah, that's a good segue to Sivan's talk.
I have a question. Do we expect, and if so, why, all neutron star cores to have the same equations of state?
That's a good question. So there are 2 things that come into play here. So one is just the fact that, obviously more massive neutron stars can reach higher densities in their cores, and therefore, maybe at their very interior, the equation of state, you can only probe the equation of state up to a certain density. And if you have 2 solar mass neutron stars versus a 1.4 solar mass neutron star, maybe you probe a higher density where the equation of state is now different. That's one thing. But the other thing is thinking about whether or not you can have phase transitions, and then the evolutionary pathway to form neutron stars can potentially have you on one branch of the phase transition versus the other branch. And I know there are people who think about that, but by and large, I think phase transitions are certainly a reasonable thing. It's not unreasonable and perhaps even likely that there are phase transitions inside the cores of neutron stars, but I think it's very hard to come up with an evolutionary pathway where you get one neutron star landing on one branch and another not. It just seems, I've never quite understood how that's possible, but I know people work on that.
Crashing 2 of them together might be one way to trigger another branch.
Potentially, yes.
Okay. Any other questions? everyone. I don't see anything in the chat.
Oh, it's late for you guys. I'm surprised that you even have your seminars at 5 p.m. If we had seminars at 5 p.m., the attendance would be like 3 people.
It's 10 a.m. U.S. Eastern.
Yeah, no, I understand.
And we couldn't push it any earlier because West Coast people like you will then have to kill us or stay up all night.
I'm
Okay.
right now.
What was that?
Sorry, I didn't hear that.
What is the time now in the West Coast?
Oh, now it's 8 a.m. Yeah, we started at 7.
It's fairly early. Thanks very much for coming
Yeah.
up so early.
It's a great sacrifice
my
for science.
My pleasure.
Thank you. Thank you again.
Thanks for having me.
I'm-
Yeah, sorry, I hope to visit in person next time that's
No.
possible to
Thank you,
actually fly
Ben.
in.